Hi, my name is Connor McHugh, and today I'm going to be talking about a research paper titled Be Sensitive and Collaborative, Analyzing the Impact of Coverage Metrics in Greybox Fuzzing. So this is a presentation on the paper by multiple different authors, and it's presented by myself for CS 4094 at Virginia Tech for the Fuzzing capstone. So really quickly, we're just going to go over some of the contents that we're going to talk about today. So we're going to give a brief introduction to the paper, some background ideas that are kind of necessary to really understand the paper, the core idea and some of the aspects covered in the paper, the results of the paper as well, the impact it has on fuzzing, some improvements and limitations from the paper, and a general summary about what we've talked about. So going into just a little bit of introduction, at a high level, the paper really just asks one simple question, and that is, does the choice of coverage metric actually matter for fuzzing effectiveness? So Greybox fuzzing has become one of the most successful vulnerability discovery techniques in practice, with tools such as AFL and libfuzzer finding thousands of real-world bugs in everyday programs. However, despite this success, most fuzzers rely on very similar feedback signals, most commonly known as edge coverage. So the paper challenges the assumption that coverage is simply a measurement of what code has been executed. Instead, the authors argue that coverage defines how a fuzzer explores a program, and that choosing the wrong coverage metric can fundamentally limit what bugs you find. So most Greybox fuzzers, including AFL, implement coverage tracking using a shared memory bitmap. So during execution, each control flow edge would update an index in this bitmap using a hash of previous and current basic blocks. If an entry is updated in this way, it triggers what's considered an interesting bit, and it's added to the fuzzing queue. And this mechanism kind of allows fuzzers to monitor coverage with little to no overhead while still guiding the input mutations. So I know that was a lot. And to fully really understand what I'm talking about, I'll explain a little bit about the background for fuzzing. So fuzzing in general is the process of generating inputs in order to find bugs or crashes in software. So in black box fuzzing, the program is treated as completely obscure, and inputs are generated randomly with no knowledge of internal execution, which is my demonstration of the blindfold. And on the other hand, there's something known as white box fuzzing, which uses techniques such as symbolic execution or constraint solving to reason about program paths. However, these approaches are both computationally expensive. So Greybox fuzzing sits kind of in the middle of black box and white box fuzzing. In Greybox fuzzing, the target program is instrumented in a way that the fuzzer has lightweight runtime feedback and most often has coverage information. The fuzzer has the ability also to mutate existing inputs and keeps those that trigger new program behavior. And this is kind of detailed with the whole map here with the seed selection, the seed scheduling, the mutation, and kind of going through that roadmap of hitting something and getting this new coverage and creating a new seed and adding it to that queue. So coverage acts as the fuzzer's notation of progress. When an input increases coverage, it's considered interesting and it's used as a seed for future mutations. And traditionally, this coverage signal is what's known as edge coverage, which tracks transitions between control flow graphs. And edge coverage became popular because it's easy and cheap to track and generally correlates well when you explore new parts of programs. However, the key question that the authors ask is whether edge coverage is actually the best signal for guiding exploration. One important detail in the paper is that coverage metrics define how execution traces are distinguished from each other. So two program executions that have the same control flow edge will appear identical under edge coverage, even if they manipulate data differently. This means that important behavioral differences in the program might not be visible to the fuzzer if the coverage metric is too much. And again, I know this is a lot, so to try and make this a more concrete thing, we can walk through a bit of an example. So we can think of a program that would process image files. The fuzzer might start with a valid image as a seed input, and from there, it would then mutate small parts of the file. Might flip a bit, insert bytes, or delete some data. And some of these mutations will cause the program to crash. Others might cause the program to execute new code paths that have not been explored before. And when a fuzzer detects new coverage, that mutated input then becomes part of the seed pool, and it's used to generate additional mutations. So also one question I'd like to pose, if edge coverage has already been successful in modern fuzzers like AFL, what do you think motivates researchers and people who have a genuine interest to look for alternative coverage metrics? So moving on, the central idea of the paper is attempting to almost reframe kind of how we think about coverage. Most fuzzing research treats coverage as the primary metric for evaluating how much of a program has been explored. The authors of the paper here instead treat coverage as feedback that actively shapes the fuzzer's behavior. And they introduce two important properties of coverage metrics, sensitivity and sparsity. So in the paper, they're described as follows. Sensitivity refers to how easily a metric detects differences in execution. And so a highly sensitive metric will treat small changes in behavior as new information, while sparsity refers to how often metrics produce new signals. So sparse metrics produce new signals rarely, which can cause exploration to slow down. The authors argue that these two properties interact in important ways. If a metric is too sparse, the fuzzer might stop making progress because it doesn't observe new coverage. On the other hand, if a metric is too sensitive, the fuzzer may become quickly overwhelmed with signals that really don't do much in helping guide exploration. So understanding this trade-off is very key to understanding the paper. So, for example, if you just imagine two inputs that follow the exact same control flow, but operate on very different data values, under edge coverage, these two executions would appear identical because the same control flow edges are taken. However, if we tracked comparison operations or memory access, which we'll get to, the fuzzer could detect that the executions are actually different. And this kind of illustrates how more sensitive metrics can reveal behavioral differences that some of the simpler metrics can't detect. So in the paper as well, the authors go into what's known as a sensitivity lattice, which they had this diagram in the paper. It is very complex, and we'll cover some of this stuff in it later on in the presentation. But to describe this relation between coverage metrics, they introduce the concept of a sensitivity lattice. Basically, one coverage metric is considered more sensitive than the other if it can distinguish more execution behaviors. So one that tracks a full execution path is more sensitive than one that can only track the edges. However, not all metrics can be directly compared. Some may detect different types of behavior rather than strictly one or a few. So because of this, they form a partial ordering structure, which is the lattice, rather than just a simple, 1, 2, 3 ranking. So what the paper actually does, the authors performed a systematic study of different coverage metrics. They implement and evaluate several types of coverage signals, including traditional edge coverage, block-based coverage, path-related metrics, context sensitivity metrics, and comparison-based feedback that tracks the outcome of program comparisons. So once I have that, they then run fuzzing experiments across a range of real-world programs, and compare how these metrics influence exploration and bug discovery. So one of the most important results of the paper, which we'll talk about a little bit more in the end as well, is that no single coverage metric consistently performed the best across all cases. Different metrics guide the fuzzer towards different execution behaviors. So some metrics help the fuzzer explore new control flow structures, while others help it to uncover subtle semantic differences in the program execution. One of the most interesting finds is that the authors observe that different metrics tend to discover different bugs. And one of the more technical metrics introduced in the paper is memory access coverage, which was part of the lattice structure that we covered on the last slide. So instead of only tracking control flow transitions, the authors use memory operations as well. Each access is represented as a tuple with the access type, memory address, and branch location where the access occurs. And in the paper, they use different abbreviations and symbols from it. In order, it's known as type, address, ADDR, and then block transition as block_trans. So to efficiently track these types of accesses, in the paper, what they do is they hash them into the same type of bitmap used in traditional fuzzers. And then the hash combines these branch flow identifiers with the memory access pattern. And the authors also separate read and write accesses by mapping them into different regions of the bitmap, which allows the fuzzer to distinguish memory from reads and writes while maintaining that tracking. So again, this is a lot. For an example, if you imagine a program that writes user input into a buffer, two inputs might follow the same control flow path, but write to different memory locations. So under traditional edge coverage, the fuzzer would not distinguish between these executions. However, with memory access coverage, the fuzzer records the memory address involved in the access along with the branch location where it occurred. So by hashing this information into the coverage map, the fuzzer can recognize that these executions are meaningfully different and continue exploring mutations based on those inputs. Now, really get into one of the core ideas of the paper. The authors propose the idea of collaborative coverage. So instead of trying to determine which metric is the single best choice, they allow multiple coverage metrics to operate simultaneously. So in this approach, an input is considered interesting if any of the metrics report new behavior. So this allows the metrics to complement each other rather than work against each other. So structural metrics like edge coverage help guide broad exploration of the program's control flow, while more sensitive metrics capture subtle behavioral differences, which goes back to that sparsity versus sensitivity detail that we talked about a little bit ago. By combining these signals, the fuzzer gains a better understanding of program execution and can explore more effectively. So reiterating it, the key idea explored here in the paper is that coverage metrics should collaborate rather than compete. So in their implementation, each metric generates its own feedback, but the fuzzer shares the same input queue and mutation engine. So when an input produces new coverage in any of the tracked metrics, it's preserved for further mutation. And this allows exploration strategies of different metrics to reinforce each other rather than replace one another. So, question I'd like to propose as well, is coverage even the right abstraction for guiding fuzzing, or are there better forms of feedback that we could use? So continuing on to some results, to evaluate their approach, the authors conducted a bunch of experiments across several benchmark programs. They compare fuzzing performance using individual coverage metrics as well as a combination of the metrics. In the paper, they focused on three main outcomes: coverage growth, the time to discover bugs, and the total number of bugs found. So the results described show that collaborative coverage consistently improves fuzzing effectiveness compared to using just a single metric. So in particular, the combined approach tended to discover bugs more quickly and find a larger number of bugs overall. So one important topic described in the paper is that the different methods used are not set to be redundant, meaning that they don't really do the same thing. They kind of complement each other. They capture complementary aspects of program behavior, which explains why combining them leads to different results. So the paper didn't intend to have these metrics run the same thing over and over, but be more targeted and specific. So when run in combination with each other, they have these improved results because it wasn't a wide coverage. So across the evaluation benchmarks, the collaborative approach demonstrated that both faster coverage growth and improved discovery rates happened when the metrics were combined. The results suggest that different metrics guide the fuzzer towards different regions of the program's execution space, which allowed the combined system to explore more diverse behaviors rather than any individual metric would by itself. So the paper is important because it really does aim to challenge a long-standing assumption in fuzzing research, which is that edge coverage alone is sufficient enough as a feedback signal. By analyzing the properties of coverage metrics and demonstrating their complementary strengths, the authors provide a new way of thinking about fuzzing feedback. Their work helps explain why recent fuzzing tools have begun using better feedback signals like comparison tracing and context-sensitive coverage. So more broadly, in the scope of it all, the paper really shifts from asking, which coverage metric is best to asking how multiple feedback signals kind of work together to best work through a program. So despite its contributions, the paper does have a couple limitations that I feel are necessary to share. So the first is that the set of metrics evaluated is relatively limited. There are many possible feedback signals that could be explored, some of which include data-centric ones or more domain-specific metrics. So, for example, programs that heavily manipulate structured data may benefit more from data-sensitive metrics more so than control flow metrics. Second, the paper doesn't really deeply analyze the performance overhead associated with more complex instrumentation. So increased feedback sensitivity may introduce runtime costs that affect scalability in the future. There wasn't much detail into how the combination of different coverage metrics and techniques used would affect the overall overhead of a program and how it would be scaled in the future. Next, the strategy for the combining of the metrics was fairly simple. The paper didn't really explore adaptive approaches. In this way, the fuzzer could be able to dynamically prioritize different metrics during execution. From there, new conclusions could have been drawn based on how the metrics performed. So like previously mentioned with the feedback, if a program was more data-centric or domain-specific metrics, having the fuzzer kind of dynamically adapt to that and use different metrics to improve code coverage and actually finding more bugs. It'd be really cool to see if they could figure something out with that. And finally, one of the main issues that I had with the paper is that the evaluation focused mainly on the number of bugs found. It would be really, really interesting to see as well the severity or exploitability of the bugs found. By utilizing an outcome like this, the paper might be able to explain or highlight metrics that would be better identifying critical issues rather than just a numbers game, essentially making it a quality versus quantity experiment this is something that I really thought the paper could do better. I'd be really interested to see kind of instead of just very, very small bugs to very, very large bugs that would impact a program in different ways. They were all kind of grouped together as one, and it didn't really expand on that. So I'd be interested to see kind of what metric found what bugs, if one was better, if one was more sensitive in finding these smaller bugs, or if one was better at finding these larger bugs. I think that could be a great section to be added to the paper. But keeping those limitations in mind, the paper overall introduced a good conceptual framework. But like everything, there's always room for improvement and areas for further research, which I described with some of the limitations and the critique of it. So kind of going through these limitations and critiques, I had two questions. So in this age of machine learning and AI, I was curious if machine learning techniques could be used to kind of automatically learn useful feedback signals instead of designing them manually. So having a fuzzer with some machine learning capabilities and feedback implemented in, so as it starts running through multiple programs, it starts to learn a little bit about what causes these bugs and can dynamically shift itself to use data-centric, dynamically structured feedback, control flow metrics to really hone in on the program instead of just having it programmed manually. And the last one I had kind of goes hand in hand with it was, should fuzzers dynamically adapt which coverage metrics they prioritize during exploration? So kind of with that machine learning a bit, could the fuzzer essentially shift itself to be more data-centric, more flow structure-centric, and kind of get it where the program is the one that it's taking a look at, and it can really identify what it's supposed to look at, change its coverage metrics based on that, and then have a better experience from there. So in summary, here are some of the key ideas from the paper. The paper itself details that coverage should be viewed as feedback that guides exploration and not really just a measurement of progress. Also explores different coverage metrics and how these different coverage metrics can capture different aspects of program behavior. One of the overall topics discussed as well was that allowing coverage metrics to collaborate can significantly improve fuzzing effectiveness, which is something that I found interesting. And like anything, the paper, of course, did have some limitations and areas of improvement. Like I mentioned before, some of the metrics evaluated are relatively limited. There wasn't really a deep analysis of performance overhead when combining the different metrics. And like I said before, it'd be really, really cool to see if the fuzzer could be dynamically made so that it adapts to what program it's running against and draw new conclusions from there. But overall, the paper provided a useful idea and framework for thinking about how feedback signals and coverage metrics can have influence on the behavior of modern fuzzers, and definitely has a new perspective into how you can use coverage metrics to determine the output and find bugs, critical bugs in your program. Thank you.